now that we have an overall feeling of what an overall understanding of what electric flux is, it's time to look at the electric flux, not just through one flat surface, but over a closed surface. So what this means is that we can take advantage of how we've defined electric flux. Imagine you had a sheet of paper just like in the previous video, but now you wrap that sheet of paper into different shapes, or you morph that paper into different shapes to create a closed surface that surrounds a charge or doesn't surround a charge. But essentially the main thing is we can create an imaginary closed surface around any charged object or around any charged object and analyze the electric field at those areas. So we're going to take a look at some different shapes and what happens if we envelop a charged object or have that arbitrary imaginary shape be outside of a charged object. As I've explained, we now need to expand from surfaces to objects. So what if we wrapped a surface around a charge? So it would almost be like wrapping our surface around that charge to see how many field lines penetrate the surface. And this is going to lead us to Gauss's law, which describes what happens to the electric flux over closed surfaces only. So we are going to take a look at a few different shapes just so that we can calculate the electric flux for different scenarios. So I want to mention we can choose arbitrary closed surfaces of certain shapes to encompass our charged object. And let's take a look at some examples. So the first one we want to look at is a closed sphere around a point charge. So just remember, although we can choose arbitrary closed surfaces of certain shapes, there are some that we are going to have to use and some that are going to be quite obvious. So for a point charge, let's draw this out. We want a closed sphere around a point charge. So we have plus Q. I know that there's going to be electric field lines radiating out of charge Q. So I draw a few of these. So these are my electric field lines. And I have a closed sphere that I have to draw. So the closed sphere, I'll just draw one over here that's got a smaller radius. And I'll draw another one with a larger radius. And I want to explain what I'm trying to do. So we're going to say if we place a Gaussian sphere around the point charge, we know that the electric field decays as 1 over r squared. So that means there are less field lines for a sphere of radius 2r, for example, than the sphere with a radius of r. So that makes sense. The farther away you get from the point charge, the smaller the magnitude of your electric field. So the number of field lines that are going to penetrate the same amount of surface for the 2r sphere is going to be much less than the one that penetrates the same amount of surface for the r sphere. So now, even though I've drawn this out, the next question is, how can we find the total flux on the closed sphere? So I know that my point charge radiates electric field lines outwards. So I want to see how many of those electric field lines penetrate through that whole entire closed sphere. So in order to do that, I have to apply the equation for electric flux, which is the integral of E dotted with ds. So in order to do that, it means we have to find ds, and we also have to find E, and they're both vectors. So first, the electric field at every ds is going to be defined as E equals to kq over r squared r hat. And just to explain this, I'm just going to use the 2r sphere as the example because it's bigger and I can draw a better diagram with that. I have a sphere and I'm only looking at the surface. So I call the surface ds, and I know that there's going to be a ds vector pointing this way. So I know the electric field points radially outwards. I also note that the electric field is parallel to ds. Okay, so I know the electric field is defined as kq over r squared, or we can also write this as, just remember, k is also equal to 1 over 4 pi epsilon naught, and then r squared r hat, just for practice, 4 pi epsilon naught. So we have the electric field. Now we have to figure out ds for a spherical surface. And we've worked with cylindrical and spherical coordinates already. We know that for spherical coordinates, ds is going to be equal to r squared sine theta d theta d phi. And because ds is a vector, I have to also make sure to state the correct vector, which is r hat, as it points radially outwards, and r hat is simply this unit vector here. So it seems like I have my vectors for E and ds, which means I can now finally solve for the total flux. So putting all this together, I have the differential flux defined as d dotted with ds, which is equal to epsilon naught E dotted with ds. And just remember, there are two different ways of expressing this, and d is equal to epsilon naught E. I just want to mention d comes in handy when we start discussing materials. So with this, I now have d phi is equal to epsilon naught. I know E is equal to Q over 4 pi epsilon naught r squared. R hat dotted with ds, which is r squared, sine theta, d phi, r hat. So that means d phi is equal to Q over 4 pi r squared. Actually, I can remove the r squared because they just cancel out. So let's just cancel things out first. R squared, r hat dotted with r hat. Cosine of 0 is 1, and then both of these are unit vectors, so they just become 1. So I can get rid of those as well, and I end up with Q over 4 pi sine theta, d phi. Okay, so all we have to do now is integrate both sides and then figure out the bounds. I know that for theta in spherical coordinates, it's going to go from 0 to pi, and phi is going to go from 0 to 2 pi. So I will be able to calculate my total electric flux, can factor out the Q over 4 pi, integral from 0 to 2 pi d phi, integral from 0 to pi of sine theta d theta. And when you work this out, you get Q over 4 pi times 2 pi times negative cosine theta from 0 to pi. And the answer is going to be Q. So this is very interesting because we can conclude that the electric flux is just the enclosed charge within our surface. So now we figured out what happens when we have a closed sphere around a point charge and what the electric flux will be. And it's simply the enclosed charge Q. So then let's take a look at another example. What happens if we have a closed surface that doesn't have any charge, but in fact the charge is outside that closed surface? So we've considered an option where the charge is inside our surface. Now let's take a look at a charge outside a closed surface. So just to make things simple, I'm going to keep to the same spherical nature in terms of our shape. We're just going to have our point charge over here, which we'll call Q, and it's going to have electric field lines that radiate out of it. And actually, before I draw these electric field lines, I want to draw the shape of my closed surface. So the shape of my closed surface I've chosen so that it kind of follows the general shape of a segment of a sphere. So like that, this is like a spherical wedge, and I can call this side A, and I can call this side B. So now I can draw my electric field lines. So this one goes like this, penetrates the surface, goes in, and then comes out. So we have our electric field lines here. So let's start writing some of what we're trying to do. So what if our charge was outside our closed surface? We note that ds, so we're going to say that ds is going to be parallel to n, which is the surface normal vector. And where is ds in all of this? I have my closed surface, but my closed surface isn't a continuous shape. It's got a few faces. It's got the 4 sides, and it's got the top and bottom A and B. So that means it has 6 different faces we have to consider for electric flux. So the ds is actually going to be unique to each face. ds for A points this way, so that's dsa. ds for B is going to point this way. And then we have ds for the sides. So I'll just use this as an example. ds, s for the side. And let's do a quick analysis. The 4 faces or sides have an electric flux, so of something. So why don't we take a look? On the sides, the electric field lines are going to just be perpendicular to the ds. So let's redo our analysis. The 4 faces or sides have ds being perpendicular to the electric field. So the electric flux of the sides must be 0, because cosine of theta, or cosine of 90, is going to be equal to 0. So just to write this out, we have the differential flux element being equal to E ds of the sides cos theta, and it's equal to 0 because cosine of 90 is 0. The top face A has dsa being parallel to E. So that means the differential flux element for A is going to be equal to E dsa cosine of 0. which is equal to E dSA. And if we integrate that, we get the total flux of A being Q over 4 pi epsilon naught of the integral of sine theta d theta d phi. So that's just a simplified form. What this means is we'll be able to calculate the flux going through face A. Now we're still missing a piece. It's the bottom face. So the bottom face B has DSB. Although it's parallel, it's actually 180 degrees from the electric field line. So that means d phi b is equal to E dsB cosine of 180, which is equal to negative E dsB. So here it's important to note I have positive E dSA, and here I have negative E dsB. In this case, I can say that the total flux across B is Q, or negative Q, over 4 pi epsilon naught, the integral S sine theta d phi. So then, I want to calculate my total flux. I have to consider all 6 sides. So the total flux is going to be equal to 4 times the flux of the sides, because there's 4 sides, and we're assuming all 4 of the sides are equal in area. Although I didn't really draw it like that, but we're just going to assume all 4 sides are equal. So that plus the flux going through A plus the flux going through B. We know that this is 0. We know that this is E dSA, and this is minus E dsB. But what's also important to note is that the closed surface that I have is small. And so dSA is going to be a very small element, and we can consider both of those equal to each other. So that means I can simplify this and have E ds minus E ds, which is equal to 0. And therefore, I can state that the electric flux is 0 when the charge is outside the surface. So that's also important, another important thing to note. Something else that's important is the idea of positive and negative electric flux. Looking at the diagram again, and also our definition of flux, flux is positive here, and it's negative here. But what do you notice? If I take a look at face A, the electric field lines are coming out of the surface, and that's when flux is positive. So I can state that electric flux is positive when it exits a surface. And if I take a look at face B, so the bottom part, the electric field lines are going into the surface, and that's going to be pointed in the exact opposite direction as the surface normal vector. So that means it's going to be negative when it enters a surface. So this is very important to remember. So we've gone through what happens when we have a closed sphere around a point charge, and what happens when the charge is outside of a closed surface. Now we want to consider a more general case. So 3, this is the last one we want to go through. What if we have a charge inside an arbitrary closed surface? So in this case, I have a charge Q, and originally what we had done in part 1, we had chosen a spherical surface to envelop that charge, and that also meant we would be able to find the electric flux across a surface ds over here. But now, what if we had a surface like this? So some random arbitrary shape. That means I have to consider some arbitrary shape, like arbitrary ds that kind of looks like this. I'm just drawing this much bigger so that we have a good understanding of how we do these calculations. I have something like this, which we call ds. We have the surface normal vector pointing up, right? And then we have our electric field. So we have this electric field line going through, and it's a distance r away. Now it's also good to note that there is an angle between ds and E, and we're going to call this phi. And that phi means that we can project this entire ds onto a spherical object. So we're going to assume that this phi is equal to this phi. And that means this is ds cos phi. Just as if it was a right angle triangle like this. So to try and picture this a little bit better, we're just going to write down a few points. If we look at a charge inside a non-spherical surface, we're going to claim that the electric flux is the same as that of the inner sphere. So looking at this diagram, we know ds is parallel to the component of the electric field that is normal to the surface. And this makes an angle phi to the electric field line. Oops. This means that the projection of ds onto the inner spherical surface is ds cos phi. But when we're talking about differential surface elements, when we want to integrate that, we're taking very, very tiny pieces of that surface. So we note that the ideal value of ds is going to approach 0, and therefore, because of that, phi is also going to approach 0, and as such, we can assume that they are the same. And therefore, the electric flux is still just Q enclosed within any closed surface. And this kind of knowledge will help us build Gauss's law in the next unit.